Let's take a look now at example number 3. A ball, 1.8 kilogram mass ball, is being swung in a vertical circle at the end of a 1.2 meter long rope. And we've got the ball traveling in a counterclockwise direction here. We can see this. So from this position, it's going to move around like this. And part A here is what's the minimum velocity the ball can have at the top of its path. And part B is what is the tension in the rope as the ball swings past the bottom of the path here at 5 meters per second. So we'll take each of these in order and go from there. So first of all, what is the minimum velocity the ball can have at the top of its path? Well, if it's going to be traveling in a circle, it needs to have some sort of centripetal force, and as we stated just a few moments ago, one of those forces can be gravity. Another force may be the force of tension acting in that rope that's pulling down on it. And this, we would certainly need both of these if the ball was traveling fast enough. The problem itself seems to suggest that there's some minimum velocity the ball will have, and that will happen when there is no tension in the rope. In other words, the only centripetal force that will be acting will be the force due to gravity itself. And we can calculate what that force is, or rather what the velocity is, by simply setting force of gravity as equal to the only centripetal force. In other words, we'll set force of gravity and force tension in this direction, but we've said that the force of tension will be 0 at that minimum velocity. So the only force, the force of gravity, the only force that we have acting centripetally will be that mg. We solve that equation and we come out with 3.43 meters per second. And you might well ask, well, what's going to happen if the ball is traveling at a velocity less than that? And of course, what would happen at that point is gravity would apply a greater force than the centripetal force, and that would cause the ball actually to fall out of the loop. In other words, if it's going that slowly, it's going to fall out of the loop and come down in this direction before it's had a chance to travel the circular path. And of course, if it's greater than that velocity there, if the ball is traveling at greater than that velocity, then we'll find that the force of tension has to come into play. But otherwise, yeah, if we're not traveling at that required velocity, we're going to fall out of the loop. So that's the minimum velocity the ball can have and still maintain its motion. The second part of this is what is the tension in the rope as the ball swings past the bottom of the path? Well, now we've got a little bit of a problem here because gravity continues to pull in the downward direction. Gravity's pulling down, and there is a tension in the rope. We need the acceleration to be towards the middle of the circle, the net acceleration. So although gravity is going to be pulling down, we're going to need to have a force of tension here that's pulling up on the ball. And not only just supporting the force of gravity, but also accelerating the ball at the same time. In other words, we expect that that force of tension is actually going to be greater than the force of gravity. We can calculate that by using Newton's second law. Again, Fc is equal to mv squared over r. Notice that we've made the force of gravity negative here because it's downwards or away from the middle of the circle. Force of tension is upwards towards the circle, and by playing around with this equation and rearranging, we can see that the force of tension then comes out to be 55.1 newtons. The ball's mass itself, the 1.8 kilograms times the 9.8 meters per second squared, means that the ball itself has a weight of 17, a little more than 17 newtons. Notice that our force of tension is much greater than the 17 newtons that the ball weighs. Why is that? Because we need an additional force of tension, not only just to support the ball's weight, but to accelerate it towards the middle of the circle, to support its weight as the ball moves past the bottom of the circle.